Last time, we introduced electrical systems, voltage, charge, current, and the constitutive laws that relate them. What principles do we use to generate mathematical models of electrical systems? In the case of mechanical systems, the principles we used came from Newton's laws. In the case of electrical systems, the laws we use are Kirchoffs laws. Kirchoffs laws come in the form of two statements: Kirchoff's current law, which will denote KCL, and Kirchoff's voltage law, which we denote KVL. The current law states that the current into a node, a place in the circuit typically where two wires meet, so it might look like this, where we have two wires meet, but the node could be anywhere, but we'll typically choose it to be right where they meet, must be equal to the current out of the node. So if we have current coming into this node, then that must be equal to the sum of any currents that are exiting it. So therefore, KCL says that the sum of the current in must be equal to the sum of the current out. Kirchoff's voltage law states that the sum of the voltages around a loop must be equal to 0. Let's focus on the voltage law first and look at an example. Let's say that we have a capacitor and resistor and a battery in a single loop. So we have a capacitor, a resistor, and a battery. We can choose to have the current running counterclockwise in the loop. And that determines the polarities of the elements. So here I have a plus sign, and here I have a plus sign. But remember that the battery, because the large dash is right here, that positive terminal must be there. If we evaluate the voltage law clockwise, starting at the battery, and assign negative signs anytime we encounter the negative sign of an element, we get VB minus VR minus Vc is equal to 0. And if we now substitute the constitutive laws for Vc and Vr, where, just to remind you, Vc is equal to 1 over Cq, and Vr is equal to Ri, but that's equal to R Q dot. We find that Q dot is equal to minus 1 over RC Q plus VB over R. This is the same differential equation as the spring damper system with an external force. So you can think of this as being a wall, a spring, a damper, and an external force. It is a linear, constant coefficient, first-order ODE, so we can use all the same tools we used for mechanical systems, including Euler integration, analytical solutions, superposition, and convolution. Let's look at a slightly more complex example that focuses on Kirchoff's current law. So if I have a capacitor, a resistor, and a battery in between them, in the way that I have drawn the current flow conventions, Kirchoff's current law tells us that the current into the node must be equal to the current out of the node. So at node 1, we know that I sub C is equal to I sub R plus I sub B. And at node 2, we know that I sub R plus I sub B is equal to I sub C. So the two nodes give us the same information. Lastly, let's look at an example that combines KCL and KVL. This example has 3 capacitors and 2 resistors. So we have a capacitor, another capacitor. At the end, we have a resistor. And then all the way at the other end, we have a resistor. And in between, we have 2 capacitors. I'm going to use the same current flow notation that I used before. And it has to be consistent with the current flow notation on the bottom. Now this also determines the polarity of all the elements. So I have a positive sign here, a positive sign here, positive sign there, a positive sign here, and a positive sign there. Now I've completed the diagram. I can assign the current flow convention any way I want, and once I've done so, I can evaluate Kirchoff's current law. And I get that I C2 is equal to I C3 IC4. So I'm going to go ahead and label each one of these so that we don't forget which ones are which. And this implies that QC2 is equal to QC3 plus QC4 plus some constant. But we're going to assume that that's equal to 0 because typically the total charge in a circuit is equal to 0. This equation implies that QC3 is equal to QC2 minus QC4, and we're going to use that in a moment. Now, the Kirchoff voltage law implies that VR1 plus VC2 plus VC3 is equal to 0, and it also implies that VC4 plus VR5 minus VC3 is equal to 0. From these, I can conclude that R1 IR1 plus 1 over C2 QC2 plus 1 over C3 QC3 is equal to 0. I can also conclude that 1 over C4 QC4 plus R IR5 minus 1 over C3 QC3 is equal to 0. Now, if I substitute in for Q3 and note that IR1 is equal to QC2 dot, that's because of this node here. And if I note that IR5 is equal to QC4 dot, that's because of this node, then I get that QC2 dot is equal to minus 1 over R1 C2 QC2 minus 1 over R1 C3 times QC2 minus QC4. The other equation that I get is QC4 dot is equal to minus 1 over R5 C4 times QC4 plus 1 over R5 C3 times QC2 minus QC4 again. This is a linear, constant coefficient, first order ODE. I could write this in vector and matrix notation by choosing the state to be W equals QC2 and QC4. Lastly, what is this system similar to in terms of a mechanical system? Capacitors are like springs and resistors are like dampers, so we might expect 3 springs and 2 dampers. Indeed, the mechanical system that corresponds to this differential equation is a spring, a damper, they're connected by a spring, and then there's another spring and damper on the other side. Now this gives us the same ODE, but with potentially different coefficients, depending on the spring constants and damping constants. So what should you remember from today? Kirchoffs laws provide the principles by which we construct ordinary differential equations that predict the evolution of charge in a circuit. We also learned that electrical systems often have mechanical analogs, as in the last example. But what if that mechanical analog has masses in it? What electrical system would behave in the same way? Next time, we will talk about inductors and how they complete the analogy between electrical and mechanical systems.